Hello everyone, welcome back to the NPTEL course on materials informatics. In this lecture we will continue our discussions on statistical mechanics. Just as a recap of what we did in the previous lecture, so we looked at statistical mechanics as a bridge between microscopic interactions that occur at the atomistic or electronic level and macroscopic thermodynamics, which define equilibrium, phase stability of your system. So it can basically act as a bridge between theory and experiments, theory which sort of governs microscopic interactions and experiments at the macroscopic scale. We took a brief primer on thermodynamics, so we looked at different thermodynamic potentials, Legendre transforms, properties of a system, their differential forms and so on. We also looked at a brief primer on quantum mechanics, time independent Schrodinger equation being the key, and we looked at solutions for 1D box as well as 3D box. And then the main mathematical framework on which statistical mechanics lies, which is the ergodicity principle or ergodicity postulate, which basically states that time averaging and state averaging, as long as the time averaging is done over long time scales and state averaging is done over large number of states, should yield the same macroscopically averaged quantities for a given system, right. So that is the ergodicity postulate. So this postulate holds true for most systems. So there are systems that sort of violate this ergodicity postulate as well, but for more material systems, most materials systems, the ergodicity postulate is is valid, and hence we can use the remainder of statistical mechanics to basically predict macroscopic properties. So in this lecture we look at a few example ensembles. So recollect that ensembles are basically your collections of copies of your system or collections of microstates, and whenever you define a property for an ensemble, you basically define the macroscopic property or the property for the macrostate, right. So we look at a few example ensembles in statistical mechanics that is often used to model systems under different boundary conditions. Okay. So the most common or the most trivial example of an ensemble is basically your microcanonical ensemble, right. This is used to model isolated systems. So in macroscopic thermodynamics also, right, isolated systems are very popular because whatever you prove for an isolated system basically holds true for your universe, because your universe is an isolated system, right. So whenever you hypothesize a behavior of some quantities, this could be entropy, this could be internal energy, this could be temperature, you try to see how it behaves for an isolated system so that you get an idea of how it should behave across the universe, right. So since this is quite popular in macroscopic thermodynamics as well, even in statistical mechanics we can start with an isolated system, right. So for an isolated system, these three quantities are constant, right. So your total energy of your system is constant, your system is not expanding or compressing, so volume is constant, system is not exchanging any species, so number of moles are constant. We are basically ignoring any other possible work terms, so we are assuming that the system is not being influenced by any electric field or any magnetic field and so on. So we are sort of ignoring other terms, but for such systems we have to generalize. So we basically have to state that the net electric field passing through the system is 0, net magnetic field passing through a system is 0 and so on, right. But if you take a simple scenario or simple case where the system is not influenced by any electric or magnetic fields, then we just need to consider these three variables. So energy, system is not exchanging any energy with its environment, system is not compressing or expanding, system is not exchanging any species, right, with its environment. And if this holds true, this is an example of an isolated system, right. And for an isolated system, basically we can create A copies of the system all under the same energy, volume and number of particles, right. So this is fairly trivial, right. So you take one system, you either you take this isolated system and then keep examining it over time, right, or you take A copies of the system, right. So if we take A copies of the system, all of these A copies should have the exact same boundary conditions. So all the copies should have the same energy, all the copies should have the same volume, all the copies should have the same number of particles, right. Now this leads to a very sort of straightforward conclusion, right. So if you think about all the copies of the system, right, or all the microstates of the system, they all have the same energy as that of the macrostate. So the macrostate also has the same energy, all the microstates also have the same energy, right, because the energy is sort of constrained for the macrostate. So when you create copies of that macrostate, so copies of your system, all the microstates will have the same energy as well, right. And if you create such an ensemble, it is basically referred to as a microcanonical ensemble, right. So in a microcanonical ensemble, if you think about degeneracy, so we define degeneracy as the number of states of a system that can have the same energy, right. So we have created A copies of the system here, right, all the copies have the same energy, so which implies the degeneracy is trivially equal to the number of copies that you have actually created. So it's trivially equal to A, right. So now we have created an ensemble, but what about probabilities? So we said that for state averaging, right, for ensemble averaging, we require the individual property in a given microstate, and then we need to weight that property with the corresponding probabilities, right. So if I were to write this briefly, so we basically said that the average property here E bar is basically summation of I over I Ei times Pi, where I is any microstate, right. So we need to know what this Pi is, right, and since we need to know what the probability is, and this probability is not straightforward to determine, right, in a microcanonical ensemble, because all the copies of the system have the same energy, have the same volume, same number of moles, basically they are all isolated. So all copies of your system are isolated. So how do you differentiate, how do you evaluate these probabilities, right, and this is where the second postulate of statistical mechanics comes in. So the first one is the ergodicity postulate, the second one is equal a priori probability, right. So what this states is that in an isolated system all microstates are equally likely, right. So in other words, the probability of all microstates, the probability of occurrence of any individual microstate should be the same as all other microstates, right. So if you think about probability of a given microstate occurring, right, or a given state I occurring here, this should be nothing but 1 over your degeneracy, so 1 over omega here, which is basically constant for all I. So you see that there is no dependence of I here, right. So the probability of any microstate in the system is just related to 1 over your degeneracy, 1 over all the copies that you have created. So this is actually a postulate, but this postulate works fairly well within statistical mechanics. So apart from ergodicity, you have this equal a priori probability postulate, right. Now if you just trivially calculate what is the average energy of your macrostate, right, so you can write this as Ei times Pi, same relation as here. So your Pi is basically 1 over omega, so you can take that out, so it is not dependent on I, so it is 1 over omega times sigma of I over all energies. So the energy of all microstates is just E, right, and if you do the summation over I copies, right, so there are a total of omega copies of your system, so you should simply get E times omega by omega, which would be the same as E, right. So the energy of the microstate is the same as the average energy of the macrostate, right. So we trivially prove that this condition is satisfied using equal a priori probability, right. So in microcanonical ensemble, this is a ensemble that is used for modeling isolated systems, and in order to predict the probabilities, we use this second postulate, which is equal a priori probability. Of course isolated systems are not super useful in terms of practical purposes, because we typically do measurements under, let us say, isothermal conditions, isobaric conditions and so on, right. So one way to sort of move away from microcanonical ensemble to model more real systems is to use a canonical ensemble, right. So here we are not dealing with an isolated system, so here the system is in thermal equilibrium with a reservoir, right. So here the number of moles of the system is constant, the volume of the system is constant, but the instead of energy, the temperature is what is constant here for the system, and hence for each microstate you have the same temperature, right. So N, V and T are the same, not N, V and E, and this temperature will be the same as that of the reservoir that your system is under that your system is in equilibrium with, right. So basically you have one system that is in equilibrium with a reservoir at some temperature, right, and now we are modeling or we are taking several copies of that system, right. So for each copy of the system will have the same number of particles, will have the same volume, and it will also have the same temperature, but the energy of individual microstates can actually vary, right, because we are not fixing the energy here, we are only fixing the temperature here, so your energy can actually vary, right. So this will actually be different for individual microstates, which implies we now cannot apply equal a priori probabilities, right. So equal a priori probabilities is sort of holds true if you have microstates that have N, V and E as constants, right, not N, V and T, because each microstate now has a different energy, right. So how do you now calculate probabilities, right. And if you find a way to calculate probabilities, we can basically model systems in this canonical ensemble, and these systems are basically in thermal equilibrium with the reservoir. So these are not isolated systems anymore, so more practically useful. So in order to calculate these probabilities, right, so there are a lot of mathematical tricks that we will need to employ. I'll just mention the mathematical tricks, but I won't go through them in terms of their derivations in the interest of time. So briefly what we try to do is we try to create an ensemble of ensembles, right. So we first fix some kind of an ensemble energy, let us say zeta, and let us say this we fix up to be a constant, and then we keep collecting microstates within our system. So each microstate has a different energy, but we keep collecting microstates so that the summation of all the energies of all microstates add up to your zeta, right. So let us say this zeta is 100 joules, right, we can have 10 microstates of 10 joules each, right, or we can have 2 microstates of 50 joules each, right. So we just collect microstates, and then this collection of microstates should add up to the same value of zeta. Now you see that there are several possible values of zeta that are several possible combinations that can give rise to the same zeta, right. So once again, if you have 100 joules as your constant energy, then you can have 10 joule microstates, 5 20 joule microstates, or 2 50 joule microstates, right. So there are several possible combinations by which you can arrive at the same zeta, and these possible combinations, right, basically represent a a collection of microstates that have the same zeta energy, right. So you now see that we have created an ensemble of ensembles. So each zeta is a collection of microstates of different energies, and then you have a collection of microstates all of which will has an energy of zeta, right. So we have created a microcanonical ensemble of zeta energy, where individual microstates of the microcanonical ensemble are canonical in nature, they have different energies here, right. So we have basically created a microcanonical ensemble of canonical microstates. Once we do that, right, for the individual microstates that have the zeta energy, right, so for individual collections of EI, those collections will have the same probability, right, because zeta is the same for the individual collection. So for the collection of 10 joule microstates, 5 20 joule microstates, and 2 50 joule microstates, these 3 collections all have the same energy, right, which implies the probability of occurrence of these 3 states will be the same, right. We can use the equal a priori probabilities postulate. So we can do that and then try to solve for and we use some counting tricks basically to try to solve for the probability of the individual microstates that basically contribute to your epsilon, right. So just as a summary here, right, so we have summation of I EI giving rise to zeta here, right, and then we have collections of zeta, right. So this is basically our microcanonical ensemble, and this is basically our canonical ensemble, right. For this microcanonical ensemble we can use this equal a priori probabilities. So each of these states will have the same probabilities, and we can basically use some counting techniques. So for this zeta we can try to determine what should be the individual probabilities of EIs are. For this zeta we can determine what the other individual probabilities of EIs are, and so on, right. So there are some counting tricks that we can use to calculate these individual probabilities. So the mathematics is a little bit complicated, there are a lot of steps to be followed here, so I will sort of skip the math in the interest of time, and I will give you the final probability here. So the probability of an individual microstate in a canonical ensemble is basically given as e to the power negative alpha times e to the power negative beta and your energy of your microstate itself here, EI here, divided by the total number of canonical microstates that you actually get. So this is the total number of copies of your canonical ensemble that you have, right, A here, and alpha and beta are basically constant that we need to determine, right, and we will determine them very shortly. So one thing is, so we have calculated these probabilities. Now probabilities always have to be normalized. So if you sum up the probabilities of all the different microstates of your system, they have to add up to 1, right. So if you simply use this mathematical condition, we will see that your e to the power negative alpha divided by A, right. So alpha is a constant that we need to determine. A is the total number of copies of the canonical ensemble that we have actually created, right, of the canonical microstates that we have actually created. So we basically see that e power negative alpha by A is nothing but 1 over the summation of this e to the power negative beta times ei terms, right. So we this summation here, this summation in the denominator here is what is referred to as the partition function, right. So the partition function usually denoted by q, sometimes it is also denoted by z, capital Z, right. So this partition function is basically written as a summation of your e to the power negative beta ei terms here, or the summation of your individual exponential terms here, and this partition function is a key quantity. We will see that it contains all the necessary information about any ensemble, right, not just canonical, even for microcanonical and any other ensemble that we define for modeling a system. As long as we are able to calculate the partition function of that ensemble, we should be able to calculate the macroscopic properties of your system, right. So if you now rearrange the terms, we basically get the probability of an individual microstate within the canonical ensemble is nothing but your exponent of negative beta times ei and normalized by your partition function here, right, normalized by your q here. We still need to find out what beta is, but at least ei is is a property of a microstate, right. So at least here we have the probability of a given state dependent on a property of your microstate itself. So ei is a property of a microstate which dictates your probability that microstate will actually occur in your canonical ensemble. Okay. There is also a relationship between canonical and microcanonical ensemble that we can very quickly derive. So let us say you have degeneracies of a given for a given energy, we can now redefine the partition function as a summation over all the energy states, right, instead of the individual microstates itself, right. So originally we had defined our q as summation over I e to the power negative beta times ei here, right. So this was our original definition. Now if you have for any given ei, if you have degenerate states, if you have degenerate states here, right. Now instead of summing over individual states, right, we can actually sum over individual energies, right. This is actually an easier way to sum, right, because we know if we know the degeneracies already, instead of counting the number of states, you can just count the number of energies, right, energy levels that you have, and for each energy we just account for the degeneracy, account for the number of states, right. So this is a nicer way to sort of redefine our partition function, right. So once we redefine, once we include this degeneracy aspect, we can now consider this microcanonical ensemble as an extreme scenario of our canonical ensemble where all the microstates have only one energy, right. So the canonical ensemble is general enough where individual microstates can all have different energies, right. But if you now impose this extreme condition that all microstates should have the same energy, then we have basically gone from a canonical ensemble to a microcanonical ensemble, right. So in other words, we can view microcanonical ensemble as an extreme scenario or a special case of the canonical ensemble itself, right. So if you now state that all the energies of individual microstates should be the same value E, right, your partition function simply becomes now omega times e to the power negative beta times E, right, because we are summing over energy states, there is only one energy value E here, so the sum sort of disappears, right. So now if you calculate the probability, right, of any individual microstates, any individual microstate has the same energy, so it is e to the power negative beta E divided by your partition function, so that is omega times e to the power negative beta E, the exponent terms sort of cancel out, so you simply get back your 1 over omega or 1 over your degeneracy, and this was our definition of equal a priori probabilities, right. So we see that the mathematical framework that we have developed in our canonical and microcanonical ensembles are now internally consistent. Okay. So the next question that we need to understand is what is beta. So we define beta as some kind of a constant, right, and we need to define mathematically what beta is, right. Again, to do this we need to do several mathematical tricks and use some relationships that we have with macroscopic thermodynamics, right. The first thing that we need to use or understand, so I will just detail the, I will just state the steps, but I will not go through the math in the interest of time, right. So the first thing that we need to do is define or understand that our average energy is nothing but sigma I Ei Pi, right. So this is the energy of individual microstates times the probability of the individual microstates. So I can actually expand this out in a summation form like this, right. So it's summation over I Ei times e to the power negative beta Ei divided by summation over I e to the power negative beta Ei, right. I mean this is a common mistake that many students do, they try to cancel out these exponential terms here, but remember that these are within the sums, right. So you cannot cancel terms within the sum, you have to actually pull them out of the sum before you can cancel anything, right. So these two are two different sums here, right. So just like you define a average energy of your canonical ensemble, so average macrostate energy, you can also define an average pressure, right. So this pressure can be defined as pressure of an individual microstate, individual copy of your system times the probability of that copy to occur, right. And this once again can be written in the simple form that Pi e to the power negative beta Ei divided by summation over I e to the power negative beta Ei. So this is your probability term and this is the pressure of your individual microstate. So you can write these definitions for any property of a system. So the macroscopic average will be individual microstate property times the probability that that microstate will occur. So this is true for any ensemble or state averaging technique, which is what we do in statistical mechanics, okay. So now the key is now to understand that this macrostate average energy, right, is the same as what we define or use in macroscopic thermodynamics, right. So this E bar and this E are the same, right. So we can write from macroscopic thermodynamics, we can write dE equals TdS minus PdV plus mu dN. This is just the definition of our differential of our internal energy, right. And now if we take a derivative with respect to volume, right. So if you take dE dV and I am going to take the derivative under constant number of moles, so this term is going to drop out and constant temperature, right. So if I take it at constant temperature, my TdS now becomes TdS dV, so I cannot take a differential with respect to T because T is constant, right. So that term will drop out and then you have a negative P here, so the dV is actually what is differentiating, so you have a negative P. We actually have a framework in thermodynamics called Maxwell relations, called Maxwell relations. These basically do with the fact that your state functions such as internal energy are exact differentials. So E is an exact differential, right, and so are the other thermodynamic potentials such as H, F, G and so on. So if you actually take the second derivative of E, so let us say you take d square E by dV ds, right, the order of differentiation shouldn't matter, so it should be the same as d square E ds dV, right. So if you do d square E dV ds, this is probably let us say negative dP ds, right, and this is done at constant volume number of moles, and this should be the same as dt dV under constant entropy number of moles, right. So this is one type of relation that you can define using internal energy. Using the other thermodynamic potentials you can define other Maxwell relations as well, and these are always valid, right. So we use one of the Maxwell relations to convert this ds dV term into dP dt term, right. So ds dV is a slightly non-intuitive term to deal with, but dP dt is something that is more intuitive, right. So if you take a simple ideal gas system, right, you have a very nice equation of state which is PV equals nRT, so you can define dP dt very easily, right. So that is just nR by V, right. So this is a much more tractable term for us to define. So you can now write your dE dV, right, as your T times dP dt minus P, right. We can now start substituting your E here with this E bar and your P here with this P bar here, right. and if we do that we can basically get a relationship between our summation terms here, right, and the macroscopic thermodynamics here, right. If we do this exercise, so if you start substituting E with E bar here, P with P bar here and so on, you will get some mathematical constraints that have to hold true for this relation to be valid, right, and the mathematical constraint will basically turn out to be that your beta has to be equal to 1 over kBt, right, where kb is a Boltzmann constant, right. So this is a fundamental constant, right, that is well known in literature. So beta is basically 1 over kBt. So your beta is basically proportional to the inverse of temperature. So this is the sort of key takeaway message from our key understanding of what is actually your beta in your canonical ensemble. Okay. Alright, so let us now, so we have defined our alpha and beta, right. So basically we now know what the partition function is in a canonical ensemble, and hence we should now be able to make relationships with macroscopic thermodynamics, right. Now in a canonical ensemble your system is under constant number of moles, volume and temperature. So your governing potential is actually your Helmholtz energy here, right. So you can write a Helmholtz energy as E minus Ts, so and the differential form as negative SdT, negative PdV and mu dN. PdV and mu dN come from your internal energy, instead of TdS we get negative SdT, right, in your Helmholtz energy. And we can actually show, so this is a relation that holds true for for all ensembles including the canonical ensemble. We will see the generalization a little bit later. But for a canonical ensemble we can show that the governing potential, which is Helmholtz energy, is nothing but negative kBt ln of the partition function ln q, right. This is a mathematical relation that can be derived, but for now we will take it as axiomatic, right, we will take it as a postulate. So your Helmholtz energy can if you sort of expand this term, right, so it sort of looks like this, right. So it is negative kBt times ln of your q is a summation term, so it is ln of summation of I over all microstates e to the power negative Ei by kBt. So your kBt is your beta term here. You can also use this compressed form of expressing this relation, so you can write your f as negative ln q by beta. So beta is kBt, so you can also use this compressed form or compressed notation. Now you can use the macroscopic thermodynamic relations to derive other properties. So for example you can define what the entropy of a system under constant NVT is. So entropy of a canonical ensemble is, so it is nothing but negative dF dt, so it is the differential of Helmholtz energy with respect to temperature at constant volume and number of moles. So constant volume this term drops out, constant number of moles this term drops out, so it is just dF dt under constant volume number of moles is your negative S, right. So you can now define your entropy, so you know what your Helmholtz energy is through this partition function. So if we take the differential you will basically get this functional form here, so it is just kb times ln q plus the average energy divided by T, right. Why do you get this average energy? Because you have F equals E minus Ts here, right. So this E bar and this E are the same, right, both of these are the same. So if you actually differentiate your kBt ln q, right, you will get terms of the form, let me write it down. So if you write dF dt constant volume number of moles, you are going to get negative kb ln q, right, which is the first term there, and then you are going to get negative kbt times d of ln q by dt, right. And if you actually differentiate this logarithm of q, you will get a summation of this form ei e to the power negative beta ei divided by summation of I e to the power negative beta ei. So this is basically your q, and you will get Ei times e to the power negative beta ei term, and this whole quantity is nothing but your E bar, right, which is what you end up getting here. So this is a very nice mathematical exercise. I sort of highly recommend all of you to sort of do the math and sort of understand how these quantities actually come up. So you can define entropy like this, and then you can also define pressure. So pressure is nothing but your dF dV at constant temperature and number of moles. So once again you take a differential of this partition function with respect to volume. So the kBt has no volume dependence, so you just take the differential of your ln q with respect to volume here. And then same thing with chemical potential, right. So chemical potential is dF dN at constant temperature and volume, right. So once again that will just be the differential of this ln Q term with respect to number of moles, right. So you can now define a lot of nice macroscopic properties, thermodynamic properties once you know this partition function, right, and we have just defined this partition function for a canonical ensemble. Okay, let us now try to understand a little bit more about entropy. So we can also obtain entropy for a microcanonical ensemble, right, by considering what is the extreme scenario of your canonical ensemble. So we established the fact that microcanonical ensemble is nothing but a special case of a canonical ensemble. So we can try to estimate what this entropy is for a microcanonical ensemble, right. So we define entropy as kB ln Q plus E by T in our previous slide here. So Q basically becomes omega times e to the power negative beta E, right. This is the scenario for a microcanonical ensemble. So all the microstates of your canonical ensemble have the same energy. So your Q sort of simplifies in this functional form. There is no summation here. And if you actually do the math, right, if you simplify, you will get kB ln omega, and then you will get negative beta times E term times kB here. So that is just negative E by T plus this positive E by T here. So the E by T terms will get cancelled out. So your entropy gets defined as this very nice simple functional form, which is S equals kB ln omega, right. And this is actually a very famous equation, S equals kB times ln omega. This is the equation that is actually written in the grave of Ludwig Boltzmann, right, who actually derived this relation for a microcanonical ensemble. So this is a very nice relation, right. So if you think about entropy either in a canonical ensemble or in a microcanonical ensemble, we always define entropy as a property of the macrostate, right, as the ensemble average quantity, never a property of an individual microstate, right. And this is actually a very important property of entropy, right. So entropy is not defined for a given microstate. So it is only defined for the overall system, for the overall macrostate or the overall averaged, it is an averaged quantity. And the way to sort of interpret it is that entropy is basically nothing but a weighted count of the number of microstates in a given system, right. Your system has some microstates, let us say omega microstates, right. So how many microstates are actually there in a system that your system can access, right, that basically determines your entropy, right. So you can sort of think of entropy as an answer to this question, right. So how large is the space of microstates that are actually accessible to my system under given boundary conditions. So under given temperature, under given number of moles, under given volume, how many microstates is my system going to access? The more microstates my system is going to access, the more is going to be the entropy of the system, right. So entropy is basically the number of microstates that are being accessed by my system, right. And we can actually show that generally you can define entropy as this mathematical form here, which is nothing but negative kB times sigma I pi ln pi. So entropy is directly related to the probability of occurrence of each microstate, and this definition holds true for all ensembles. So microcanonical, canonical and any other ensembles that you define, right. So entropy of your ensemble of your system is basically nothing but your negative kB, this is just a scaling factor here, times your sigma I pi ln pi, right. So entropy is directly related to the probability of each microstate, right. So if there is a situation that the system exists only in one microstate, right, where pi is 1 for one microstate and then 0 for the remaining microstates, you will see that entropy is 0. So if your system is occupying one clear well defined microstate, then the system does not have any entropy, right. Whereas if let us say this system has two states, right, and it is equally likely to occur in both states, then you get an entropy value of kB ln 2, right, and so on. So if you have 3 microstates, then it is kB ln 3 and so on, right. So the more number of microstates and the more the probabilities are equal across those microstates, the higher your entropy is, right. So just to give some physical intuition, right. So your partition function basically determines the size of your state space. So how many microstates you have in your system, and your temperature basically is a handle that determines the accessibility of the microstate. So how many microstates your system can actually exhibit, can actually occupy at a given temperature. So temperature is the handle that determines accessibility, and partition function is basically determining the the size of your microstate space itself, number of microstates. So the combination of Q and T, which is basically your probability, is directly related to your entropy. And this definition of entropy has applications in information theory. So in information theory we are interested in finding out the optimal number of questions to retrieve information from a given signal. So this has applications in information theory as well. Okay, let us now check the third law of thermodynamics and whether that sort of holds true with our definition of canonical ensemble, right. So the Nernst postulate basically states that your entropy has to go to 0 as temperature goes to 0. So we will see whether that follows. But before that, let us go through a couple of mathematical steps to understand how to prove or disprove the precise nature of the Nernst postulate. So the first thing is, in a canonical ensemble, your probability of any given microstate, right, is actually independent of the ground state energy. So the ground state energy is usually the lowest energy that any microstate can exhibit in your system. So the lowest possible energy configuration of a system, we typically denote this as E naught, right. So the probability is actually independent of this E naught. So the way we can show it is, you can write your partition function, right, as basically the product of these two terms, right. So here you have a e to the power negative beta epsilon naught term, the times summation of I, e to the power negative beta times delta EI, where delta EI is nothing but the energy difference between the microstate that you are considering and the ground state, right. So for ground state this will just be a value of 1, and for the others it will have an exponent of negative beta times delta EI here, right. So when you calculate the probability of any state, right, you can now pull out e to the power negative beta epsilon beta E naught from both the numerator and denominator and cancel it out, right, and you can replace this with e to the power negative beta delta EI terms, right, in both your numerator and denominator. So your probability right of any microstate is independent of what specific value your ground state actually takes in, right. So which implies your ground state you can actually define any arbitrary value, you can set this to be 0 if you want to, right. So if you let us say have this extreme, if you now consider a special case of the canonical ensemble to be the microcanonical ensemble, you can now state that my system has ground state which has a 0 energy. So your partition function simply drops down to your omega term here, right, your degeneracy term here, right. Okay, so let's take this scenario where we have a ground state, right, of value E naught, right. So and if your ground state has an arbitrary value of 0, then the partition function drops down to simply the degeneracy of the ground state. So if the ground state is degenerate, then the partition function has a value of omega. If the ground state is not degenerate, then the partition function will have a value of 1, right. Okay, so let us now try to answer the question for a general canonical ensemble. As temperature goes to 0, does entropy actually goes to 0, right. So if we now consider a scenario where there is no degeneracy in the ground state, so there is one unique ground state that is possible. If we now calculate the probabilities, right, so let me now use the pen. So we have the probability listed as e to the power negative beta times delta EI divided by summation of I e to the power negative beta times delta EI. Now let us take the case of one of the e to the power negative delta EI terms, right. So let us take e to the power negative EI minus E naught divided by kBT, right. So this is how the exponent looks like, right. Now if your temperature goes to 0, you see that the denominator goes towards infinity, right, and if your numerator is a non-zero quantity, so if this is let us say a positive quantity, right, then your exponent will sort of drop down to 0, right. But if your numerator is exactly 0, right, then your exponent will sort of hit a limiting value of 1, right, because before your temperature term sort of diverges, your numerator term will go to 0 and e to the power 0 will be 1, right. So you would see that this probability term will be 1 for your ground state configuration and 0 for all the other configurations, right. So if you have no degeneracy, right. Your probability term will be 1 for only for the ground state configuration and 0 for all the other states. So if you now calculate the entropy, right, as a summation of pi ln pi terms, this will actually be 0, right, because for the ground state you have 1 ln 1 which is 0, and for all the remaining states you have your pi terms to be 0, your individual probability terms to be 0, and x ln x will always tend to 0 as x tends to 0, right, because your x function goes down to 0 faster than your ln x function diverges to infinity. So all the other terms will be 0, so your entropy term will actually be 0 here, right. So if you have no degeneracy in ground state, your canonical ensemble actually holds up your Nernst postulate. So as temperature drops to 0, your entropy should actually drop to 0. But if you have some degeneracy in ground state, right, then your entropy will actually become kb ln omega, right, because for omega terms, so your pi will be 1 for omega ground states, for omega number of ground states, right. So you will actually have to calculate, so you will have a 1 here, and then you will have you will have a 1 over omega here for your pi, and you will have a ln of 1 over omega for your so you will have a 1 over omega and then ln of 1 over omega, and you will basically sum over omega states, right. So if I were to write this down, your pi, if you have degenerate ground states, your pi will actually be 1 over omega for ground states, and it will still be 0 for your non-ground states, right. So you now see that you will have to do 1 over omega ln of 1 over omega summations omega times, right. So you will basically get s equals kb ln omega here, right, this is actually not exactly equal to 0, right. So you have a non-zero omega here, this is not 1, so even if you have a degeneracy of 2, you have a non-zero number here, so you have kb ln 2 here, right. So for example, so on the surface it looks like it's actually a violation, right. So your s is actually not tending to 0 as your temperature is tending to 0 if you have a degenerate ground state, right. But although it looks like a violation, in the macroscopic limit we can sort of see that your entropy is actually going towards 0. So even if you have a molar system, right, so 1 mole of particles all having the same energy, so let us say your degeneracy is actually 10 power 23, your Boltzmann constant has a value of 10 power negative 23, so you have 10 power negative 23 times ln of 10 power 23, right. So that your entropy will roughly be of the order of about 10 power negative 21 joules per Kelvin, and this is practically 0, right, in the macroscopic limit. We are not going to be able to measure an energy of this value for a 1 molar system, right. So for all practical purposes your entropy is actually 0 in the macroscopic limit even if you have degenerate ground states. Just a couple of other points to note on entropy before we close this lecture. So at low temperatures your system only resides in the ground state, so it is representative of a highly ordered system, so your entropy should tend to 0. As temperature goes to very high values, so as your temperature goes towards infinity, all the microstates of the system will become equally likely, so the individual probability terms will start converging into a constant value, right. So all the probability terms will converge into a constant value, and when that happens your entropy attains a maximum value, right. So the probability of all microstates will be a constant and they will all be equal, right. So and then your entropy attains a maximum value. At intermediate temperature your entropy will actually reach an intermediate value, so it will be between 0 and whatever is the maximum value that your entropy can attain here, right. And this has analogies to how your practical materials actually evolve with temperature. So at low temperatures you more or less have an ordered solid, so you have atoms sitting in well defined positions in your system, and that is because at low temperature your entropy also goes towards 0, right. So your system prefers highly ordered configurations. At intermediate temperature your system prefers an intermediately disordered configuration, so you can now have a disordered solid here where atoms no longer sit in their high symmetry pristine positions, and then when you go to very high temperatures you can have a completely disordered system such as liquid, right. So in general the higher the temperature the more accessible the state space becomes, more accessible the number of microstates, the higher the entropy, right. So higher temperature implies your system favors states with macrostates with higher entropies, right. So that is why as temperature increases you naturally have a transition from ordered state to disordered state to even more disordered state. The other thing to keep in mind is generally degeneracy of states also increases with increase in energy. So the higher the energy or the more in excited state configurations you go towards, the more the degeneracy of states is, the more the number of states that are possible, right. So higher the energy, the more number of states you generally have at those energies. Okay, so with that we will take a recap and close this lecture. So we looked at two different ensembles predominantly in this lecture. One is the microcanonical ensemble, which is used for modeling an isolated system, and the canonical ensemble, which is used for modeling a closed isochoric system under thermal equilibrium. We define the partition functions, and we also define this equal a priori probability postulate, which is the second postulate that statistical mechanics sort of stands on. The first one is the ergodicity postulate, second one is the equal a priori probability postulate, right. And then we also took a deeper dive into how entropy is a property of the macrostate, and how it is actually dictated by the accessibility of microstates in a given system under the given boundary conditions, and we also define entropy in this functional form, which is negative kb pi ln pi, right. In the next lecture we will actually look at some practical examples or practical systems where these microcanonical canonical ensembles that we have defined can actually be put to use. With that I thank you all for joining today's lecture. I will see you all in the next one.